So, like I said, this is going to be very similar to the one we did when you were pushing down on the scale. You have the arm; it's just a different muscle would be working in this example. So you're going to have, whoops. So this is going to be my free body diagram. I'm going to take what's to the left and just make it a simple problem with lines. That's why you just use your straight edge and try and also use a straight edge when you're doing these. So what I have in this problem is I'm going to have a force way over here, which would be the bone at the elbow joint. If you look here, what I just drew, that's this. So when this muscle contracts, pulling on it, the elbow will stay, the elbow joint will stay right there, and everything will rotate around it. So this is my natural pivot point. You still can move it. I mean, if I needed to solve for the force at the elbow joint, I would make the muscle the pivot point. But right now, that's the natural pivot point. So I'm going to have a force there down, and then the muscle contracts so it pulls up. So a very short distance away from that is going to be the muscle. Then you have the weight of the arm still. So the weight of the arm is over here. And now the ball is I'm holding the ball up, so the force of the ball on my hand, because all of these are the forces on my arm, not the forces that I apply to the ball. So the ball, if I'm applying a force up to hold the ball at that location, then the ball is applying a force down. So I have a force down due to the shot put. I think it's a shot put, right? Yeah, shot put. So there's my picture. I'm going to now have to label all these things. So I'll call this the bone. Again, you could call it U for upper arm bone, or you could call it E for the force at the elbow joint, E for elbow. And then this could be, that's a bicep muscle. I'll just call it M for muscle. Now, the other two, I know their values, so I'm not going to use variables for that, just like the last problem. It's just a waste of time to call everything a variable in these problems when we know the values. So let's see. So the arm is going to, the weight of the arm is 6 pounds, and the weight of the shot put is 16 pounds. So there is your picture with the forces. Now we want to get all the correct directions. So this amount right here is 0.9 inches. This amount right there is 5.4 inches. And this amount right there is 6.6 inches. And those are all the only numbers that are important. I don't really need to know if there's anything over here. I don't really need to know that. I just need to know from force to force, from the force the furthest to the left to the one the furthest to the right. So we sum up our torques because we know they have to add up to 0 in this example. Since I'm solving for, the good thing about this one is pound is a force. It's an English unit, but it's a force, so I don't have to convert whatever my answer get. My answer is going to be in pounds for my answer. So if I want the muscle, then I am going to make the pivot point where the actual elbow joint is, at B. So, and if you look at the picture, this one makes it go counterclockwise, and these two, right here, they make it go clockwise. So I'm going to, if that's my pivot point, that's my first one, that is counterclockwise. So the only positive one is from the muscle. So counterclockwise is positive, so that's going to be M times its distance to the pivot point, which is 0.9 inches. The other two are in the opposite direction, clockwise. They're causing clockwise torques, so they're going to be minus. So it's going to be minus 6 pounds times its distance to the pivot point. What would that answer be? 6.3. Okay, 6.3 inches. So you have to add up 0.9 plus 5.4. I can't tell you how many people in the test they're going to write 5.4. So 0.9 plus 5.4, you have to get the distance to the pivot point, not just the distance closest to the force that you have there. And then we're going to have minus 16 pounds times its distance to the pivot point, which would be what? 12.9. Because right here, this is 12 plus 0.9, so 12.9. All right, and that all adds up to 0. They're really not that time consuming when you think about it. I mean, once you have the picture, you just have, you're really just multiplying a bunch of pairs, a force and a distance. So that's why I said it's not like we have to stick with the variables, stop at the variables at the beginning of the problem, because it's not like I'm doing heavy algebra here. So solving for m, these two terms are just going to go to the other side. Because they're negative on this side, they'll be positive on the other side. So it's going to be 6 pounds times 6.3 inches plus 16 pounds times 12.9 inches all divided by 0.9 inches. And it's the 0.9 inches which gives you such a big answer for the muscle and the bone. Because when you have a force that is so close to the pivot point, you really need a big force if you're going to have to overcome these forces that are way out further. The further away they are from the pivot point, the greater the torque is. So I really need to compensate for the fact that I've got a small distance with a big force. And if you solve that, that answer came out to be 422 pounds. All right, now once you have that answer, let's say if I did ask you to solve for the bone, like I told you, you're going to get one or the other, you're not going to get both. But if I want to save myself some time, if I know that this number right here is 400. Whoa. Did I do that right? It's something, I gave the wrong number. Oh. Okay, so I gave you the answer for that other one we already did. So the answer for this one was 249 pounds. Really? Well, let me, okay, so 271. All right. Then my answer, somebody gave me the wrong answer then when I asked them for it. So 271 with these numbers. So if that is 271, well, I've got 22 here. So 22 would mean that this would have to be 249, right? Because if I add these all up, 249, 255, 271, the forces down have to also balance the forces up. That's the only force up, so they have to balance that. Right?